So I'm recording the session. So let's look at the PCA part. So we will discuss this theory part first, and then we can go to the practical part again. So you can open the notes, and I'm also sharing that here on the screen. Let me zoom in, then I'll zoom out while we are copying the code. So what is principal component analysis? That is PCA. So PCA is a dimensionality reduction technique that transforms a set of correlated variables into a new set of uncorrelated variables, so-called principal components. So these principal components are linear combinations of the original variables and are ordered by the amount of variance they explain. So by selecting a subset of the principal components, we can reduce the dimensionality of the data while retaining as much information as possible. So when we talk of reducing the dimensionality of the data, so we can think of this in simple English as reducing the number of features that we have in our data. So for example, if we had 20 features in the data set, so we can reduce these features to 5 features, and these 5 features will have all the relationships that were there in the original data set that had 20 features. And what it does is we combine all the correlated variables together to come up with 5 features. So from 20 correlated variables, we come up with 5 uncorrelated variables, and these 5 uncorrelated variables have all the details that were in these 20 correlated variables. Okay, so here we have some key concepts. So linear transformation, eigenvalue decomposition, and singular value decomposition. So you can search that out. Variance explained by each principal components, dimensionality reduction, whitening of data compression, advantages and disadvantages. So let's stick to the theory part first and discuss some of the key concepts. So linear transformation of the feature space. So what does PCA do when we talk of linear transformation of the feature space? So PCA finds a new set of axes, so which is called principal components in the feature space that are linear combinations of the original variables. So these new axes are uncorrelated and ordered by the amount of variance they explain. Then for eigenvalue decomposition and singular value decomposition. So PCA can be performed using eigenvalue decomposition of the covariance matrix or singular value decomposition of the data matrix. So both method results in some principal components. So you can research and see what this is. So variance explained by each principal component. So the principal components are ordered by the amount of variance they explain in the data set. The first principal component catches the largest amount of variance. The second principal component captures the second largest amount of variance, and so on. So if we were to create a model that can predict, so for example, if we are working on our farm data and we want to predict the yield, so the combination of variables that bring out more meaning as to how we can predict these crop yields will take the first principle, and the combination of variables that outputs the second more meaning as to how we can predict yield will take the second principal component. So that's basically what this means. So variance, you can think of variance as, so variance explained, you can think of it as the amount of info that these variables are giving you in terms of predicting your target variable. Then we have dimensionality reduction by selecting a subset of principal components. So by selecting a subset of the top principal components, those that explain the most variance, we can reduce the dimensionality of the data while retaining as much information of as possible. So this is, in simple terms, we are saying that by selecting few variables that explain the target variable more reduces the dimensions you have in your data. So you can change your data from being 20 features to 5 features. Then we have whitening and data compression. So PCA can also be used for whitening of data. So we said that when we are fitting a PCA model, we are fitting highly correlated variables and coming up with uncorrelated variables. So that is what we call whitening. So decorrelating the data, which can improve the performance of some machine learning algorithms. So additionally, PCA can be used for data compression by reconstructing the original data from a reduced set of principal components. So data compression, so here you so for example, if your data has 20 columns, you can reduce it from 20 columns to 3 columns. So which is what we call data compression. So basically what PCA does is it reduces your data from having a large number of features to having few number of features. So let's go to the practical part and see how this is done. So we will use the code that is here available in the notes. So I'll copy that and share that with you. I already know you have the link with you from the WhatsApp group description. And then we are going to use this code that is here. So I'll copy that. Then I'll create a new notebook. And this will be the PCA notebook. Then I'm going to paste the code there. So before we run the code, we are going to at least explain what is here. So for example, we are loading data from this AL and we are loading the wine data from the UCI library. So when running this, make sure your code has, make sure your laptop is connected to the internet. So then I'm going to split this code into parts. So for example, I can remove this part here so that we can check the data.head and see what kind of data we have. So we are loading data from this AL. So actually we can go ahead and open this AL here and see what we have. So this is the wine dataset. So it's saying not found. So this is the wine dataset from the UCI library. So I can open that link and search for, okay, so it's here. So it has 13 features. And I need to confirm if the data that I'm using here is same as what we have here. Yeah, so this is the same. So we have feature 1 up to feature number 13. So that's our data set. So hope you have that on your side also. And our target variable name is class. And these are our feature names. So we can check the data again and see how we can import it in Python. So this is how you can import it. So we can go ahead and update our code. So I'm going to copy this and I'm going to share it with you in the chat. And I'm going to try update my code here. Okay, so no module called UCI repo. So let me delete this. So let us just retain this because this is just for learning purposes. Then we can check the data description. So this is the summary statistics. So you can explore that. Then we can check if the data has missing values. So no missing values. And lastly, we can kind of do a pair plot with some variables and see the distribution that we have for these variables. So this is just the basic EDA part. So we've extracted the data, we've checked the data description, so checking the mean, standard deviation, minimum, 25 percentile, median, 75 percentile, and the max value. Then we check if the data has missing value. So the data has no missing values. Then we do a pair plot for this data based on our target variable. So which is the class. So this should be the class variable. And this is what we get. So we can see, like, for example, for most of the distributions that we have here. So for example, for feature 3, it's normally distributed. For feature 4, it's normally distributed. For feature 5, it's normally distributed. And these two, so this is right skewed. This is, I can say it's normally distributed. So the only issue we have here is we have lots of features and we need a way of reducing the features. So here we only plot 5 of the features. So we need a way of reducing all these features to something that's small and not really uncorrelated. So what we can do is we can create a heat map. So I can create a heat map with the correlation values. So we can have core being equal to data.core. So this will give us the correlation of all the features. Then to create a heat map, I'm going to have sns.heatmap. Then I'm going to annotate this heat map. Then for CMap, I'm going to use the Viridis. So let's run this and see what we get. So actually I can increase the figure size. So plt.figure. Then fig size, I can have a 10 by 10. Yeah, let me share this with you and then we can proceed. So yeah, these are the things we are checking. So I'll give you around 3 minutes to check what we've run here. So check the code for importing the data, the summary statistics, checking for missing values, visualize the pair plot and the heat map. Then after the 3 minutes, we can discuss this heat map and see how many features are highly correlated and which ones are not. Okay, I think we can proceed now. So if we check this heat map, so for the correlation values, you can see that for the majority of features that we have here, they are mostly, some of them are negatively correlated and some are positively correlated. So let me change the color mapping here and see if we are going to get something better. So the darker colors are for highly negatively correlated and the lighter colors are for high positive correlation. So for example, some features here. So for example, feature 13 and cultivar and our target column are highly negatively correlated. And the high negative correlation can be seen here in the class and the features column. So this is not important for us. So checking the target column, as what we need to see is how are the features themselves correlated. So for example, we can see feature 7 and feature 12 have a high correlation of 0.79. So we can combine feature 7 and feature 12 to come up with a single and correlated column. Then same here. Let's check this. Same here for feature 6 and 12. So we can combine feature 6, 7, and 12 to come up with a single column. And if we check how feature 6 and 7 are correlated, you can see they are at 0.86, so which is highly correlated. So already we've seen 3 columns that are highly correlated and we can combine them. So let's go back to the notes and see what we can do next. So what we can do next is fitting the PCA model. And to fit the PCA model, we will be required to scale the data. So let's import the code here and see what we are supposed to do. So first of all, we import from sklearn.decomposition, we import PCA. And from sklearn.preprocessing, we import standard scaler. Then we have NumPy. So we don't use NumPy here. So we can delete that. So we create our features column, which is this part. So we drop the target column, which is the class column. And then we create our target column Y, which is that class column. We instantiate our scalar, which is the standard scalar model. Then we create our X scaled data. So already I've shown you how we scale our data. So we have X scale being equal to scalar.fit transform, then we transform our X. Then we import our PCA model. So here we will have PCA being equal to PCA. So that's our model. Then XPCA should be equal to PCA.fit transform. So why are we doing the fit transform here? Is because, as we've seen from the notes, we are reducing the number of features that we have in our data. So I can add some markdown code here and say, you can think of PCA as a data preprocessing step. So here you reduce the number of features by combining them into a smaller number of features. So basically that's the main aim of PCA. So reducing the number of features in your data by combining them into a smaller number of features. Then you can print out the explained variance. So I'll cut this out and then we can run the code. So here you can see the explained variance for each column that we have here. Then we can visualize the first two principal components. And visualizing the first principal component and the second principal component, you can see there is a clear So there is a clear, so you can think this plot is an output similar to what we had in the clustering part. So you can see the classes can be clearly shown here. But if we went ahead and fitted this data as it was, so for example, checking 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 feature 1 against feature 5, you can see there was we had an overlap of the classes. So in between class 1 and class 3, we had class 2, which we could not clearly define because the scatter plot points were in similar regions. But once we've performed PCA, you can see here, we can clearly distinguish the classes. And here we have only two features in our dataset that can show us that, and that is the first principal component. So the first principal component is our first feature in the dataset, and the second principal component is the second feature in our dataset. And we've managed to reduce our data from having 13 features to having two features that can clearly distinguish between the classes that we have in our data. So our data has three classes. You can see 1, 2, and 3. And here we can clearly distinguish the three classes. So in simple terms, that's how you can explain PCA. So you are reducing the number of features you have in your data from you having large number of features to having a smaller number of features. And if we do something like x underscore PCA dot head, okay, so it's an array. If we check our xPCA array, so this is what we have. And here we have some items in. So we have 178 rows and 13 features. But the most important features are the first two features that we have in this data set, which is the first principal and the second principal component. Okay, any questions concerning that? So I'll give you time to research on PCA more and understand it even better. So let's check the other model that we can fit. So PCA explains all the other models because they work in a similar way. So we have, apart from PCA, we have LDA. So for LDA, we will just look at the theory part of it because it works in a similar way as to how PCA works. And the code example is here. So LDA is a dimensionality reduction technique used to primarily for classification tasks. So PCA can be used for both regression and classification, but LDA is for classification tasks. So it works by finding a linear combination of features that best separates the classes in the feature space. So LDA aims to maximize the between class variance while minimizing the within class variance, resulting in a more effective separation of classes compared to PCA. So if you are doing a classification task, it is recommended you work with LDA rather than PCA. So that's just the only difference you have here. So here we have the code example and some code to fit the LDA model. Let's go back to our notes and look at the last one, which is the t-SNE. So the T-distributed stochastic neighbor embedding is a nonlinear dimensionality reduction technique that is particularly useful for visualizing high dimensionality data in a lower dimensional space. So here you can see the main aspect, the main item here is visualizing. So how do you visualize high dimensional data? So you use the T-distributed stochastic neighbor embedding model. So for LDA, it's for reducing dimensions for a classification task. For PCA, it's for both classification and reduction and regression. And for t-SNE, you use it for visualizing high dimensional data in a lower dimensional space. So those are the key concepts that you need to understand here. So typically 2D or 3D. So t-SNE works by minimizing the divergence between two probability distributions, one that measures pairwise similarities in the high dimensional space and the other that measures pairwise similarities in the low dimensional space. So this is an example. So I can run this code just casually for us to see what we get. So here we are visualizing the digits data set. And here you can see we have label 0, 1, 2, 3, and 4. So for you to visualize numbers in Python, so you must have data that is in a way that these numbers are shown. So for example, if we check our X, you can see our X is an array. And for example, for this single array, if we visualize it, it gives us this 0. But how do you visualize these better? So we use the t-SNE model. So we've already imported the data, so we can copy this and fit a t-SNE model and run it and see what kind of visualization we will get after the t-SNE model has been fitted. So here we have some hyperparameters, so number of components, perplexity, learning rate, and the random states. And here you have it. So yeah, so this is how you visualize them. So for example, what we are checking here is, for example, we have these digits. So up here, when we were doing a classification task, so our data was in a 2D space. But for our t-SNE dataset, the dataset was in a 3D space, whereby we are visualizing the numbers as they are. So for example, 0, 1, 2, 3, and 4. So these are in a 3D space. So we want to visualize them in a 2D space. And what is a 2D space? So a 2D space is something like this, something like a scatter plot. And if we want to visualize them in a 2D space, so we use the t-SNE components and we convert the 3D space dataset to a 2D space. So for example, these, I don't know if it's blue or green. So this green part that is over here, we can say it's something like number 6. And this part here can be something like number 2. So something like that. And this is the work of t-SNE. So you visualize items from a 3D space to be in a 2D space. So yeah, hope you've understood how these three models work. Yeah. Any questions concerning the three models? So for this, you will require to like do more practice on it and more research on it, as these three topics that we have here are somehow complicated and majority of people don't apply them that much because the data that you have most of the time doesn't require you to like do dimensionality reduction, but I will recommend you take your time and research on these more. So maybe you can work on that tomorrow. Yeah, so let me change some few things. Yeah, we can proceed. So any questions on what we've discussed today? So on the PCA and the LDA parts.